This conference will now be recorded.
Good evening, everyone. We'll start with today's session with two topics on NLP. One is word embeddings, the other one is named entity recognition. We had done a lot of other tasks on NLP. We had started with pre-processing techniques, then we moved on to latent result analysis, which is allowing us to do topic modeling. There was a doubt on how to convert the given text into vectors. So one of the popular approach in NLP to do such things is word embedding approaches. Like if a given group of text wherein we want to represent those words into machine understandable format. So there are different ways to represent it. One of the way we had already seen term document vector, so that we had seen as a matrix of values. So here, word embedding approaches is allowing us to represent words in numeric format that could be understandable by the computers. Word embedding refers exactly like a numerical representation for the given set of words. So there are numerous number of embedding approaches are available. Each one has its own purpose and its own controversies also. Three of them are mainly used, are popularly used. They are bag of words approach, term frequency or inverse document frequency scheme. This we had a discussion already. Again, we'll see what is the difference between bag of words and TF-IDF here. And one last approach which is very popular in deep learning models are word-to-vector graph model. So we'll see one by one how we are going to embed word into numerical format into the system. What is bag of word approach?
Hello, Ambika.
Yeah, just a moment, I'm sharing it.
Okay, okay.
Sorry, I didn't notice that. The screen is shared.
Yeah. Thank you.
In the slide, what was the discussion here is word embedding approaches, which has three approaches: bag of words, term frequency, and inverse document frequency. And the last one is word to vector model. The word to vector model, which is now popular, quite used in deep learning, even in Grammarly software and many other softwares are trying to use word to vector to predict the next word what the human wants to type. Or it is going to provide us a lot of suggestions to type the list of words. So this is also one of the popular approach now in converting given words into numerical format. What is bag of word approach does? It is one of the simplest word embedding approach where we had a discussion already with the use of term frequency calculation. Here we have suppose three words which could be considered as simple sentences. Sentence one, we have I love rain and rain, rain, go away in the second sentence, and I'm away is the third sentence, let's say. This is the corpus with sentences we have. And the above sentence, we are going to embed them into a numerical format, wherein we are going to create a dictionary of unique set of words. So collectively, this corpus is going to have only 6 unique words, except rain, rain twice, and away, away twice. So, and I also we have twice. So unique words, we just select it and then it's going to form a dictionary which consists of 6 unique words out of 3 different sentences. Now, how the system is going to parse in bag of words model is, as usual, like we had seen in term frequency, it does the job of converting each sentence, what is present in the dictionary, and then it is going to put 1 for the available words, and it's going to put 0 for the unavailable words. If the word is repetitive twice, bag of words is going to count its frequency and then replace that number with 2 or 3 according to the frequency. So for the given 3 sentences, if we look at it, the first sentence, I love rain, all the 3 words, unique words are appearing only once. So first three words are represented as 111. The last three words which is not available in sentence one, so which is gonna be represented as 000. If you look at sentence 3, rain is twice appearing. The frequency for rain is going to be represented as 2 in bag of words, and then all other words according to its frequency, 0 if it is not, 1 if it is there. And third sentence is also going to be similar way done. So this is a simple, very simple approach which follows document like words as well as frequency, and then its count. Then it is going to represent in the form of matrix values. So after which we can like do the job of next level of processing with the use of these matrix values. So bag of words is one simple method for embedding the words into numerical format. And if we check out this term frequency and inverse document frequency, this we had seen a formula already. If we look at the last sentence of the slide, which indicates what is term frequency is. So this scheme is also a type of bag of words approach, where instead of adding zeros and ones in the embedding vector, here it's going to have some floating point values, because it's going to count the product of values, term frequency and inverse document frequency. So term frequency refers the number of times a word appears in the current document. It could be calculated with the use of number of occurrences of the particular word, as well as in the document how many number of total words are available. So depends on this value, term frequency would take up some floating point numbers could be represented. So there is a difference between bag of words and term frequency, where in bag of words we would be getting either a whole number or a zero. But in TF-IDF, we would be expecting some of the floating point values, because here this TF and IDF is going to be a product of two values. That's when we would add some floating point numbers that contain more useful information compared to zeros and ones. So this also we had a discussion before. In this, if we calculate inverse document frequency of a particular word, the formula is log of total number of documents divided by number of documents containing that particular word. So for an instance, inverse document frequency value of a word which is present in the second sentence rain is 0.17. Since the total number of documents is 3 and rain appears in the second sentence of the among 3 sentences, therefore log of 3 divided by 2 is going to give us 0.1760. Rather rain it was like only 2. So rather 2 we have got only 0.17. On the other hand, if you look at the word love in the first sentence, it appears in one of the 3 documents, and therefore its value was log 3, which is 0.4771. So more of IDF and a bag of words, if we compare, this is the main difference, where we have floating point numbers which will give us more meaningful or more precise information rather giving zeros and ones. And next, these two are very simple approaches. We usually follow it up. The last approach is something like which is very much useful, where deep learning things are done using word2vec model. So most of the natural language processing system traditionally work based on some atomic symbols. So let's say if encodings are done for some of the objects called cat and dog, it can have a lot of other values to represent. To represent image format, we are not going to dependent on one single value, something like 0 or 1. So we need some more information to provide meaningful information about an object. So that's when this word-to-vector model are very popular and become the need of the hour to represent most of the objects in the world. So using vector representations, we can overcome some of the obstacles, like it is a model. It's going to learn the vector representation for the objects like this, which is exist in the world, called word embeddings. For this kind of word-to-vector model, the learning models of word-to-vector representation, there are two. One is continuous bag of words and skipgram. continuous bag of words model is a learning model, will allow us to predict the target word from the source context word. If I say source context word, if the context is about a news article of a famous politician, so what all are spoken depends on that. It's going to, let's say, if a sentence is formed, and we are waiting for predicting the next word in the given sentence, then continuous bag of words is going to identify the context of the given source and then predicts the next word, and then produces the next predictions to the user. So if we see in Gmail how Grammarly works, or in Gmail itself, we have a lot of word predictions done for us. So it will provide us the next word to be typed by the user. Depends on the context, what we usually do, and it tries to learn from the context what is used in the mail communication, and it tries to identify the next word to be produced. Skipgram predicts source context words from the target words. So it is kind of inverse process of continuous bag of words model, wherein the output is given. I'm just predicting what is the input. That's how skipgram works. So in learning models, we'll just see an example also. Gensim is a package which is popular in NLP processing. It has the basic idea of word embeddings. Maybe it could select the similar context which is closer to the vector space model. From that, it starts generating all the vectors. Gensim is a free Python library. It is serving to generate a short list of most similar words or most similar articles which we would like to process in our document. And then this training algorithm were originally ported from the C package, and it has also a lot of additional capabilities to do other NLP processing also. There are two architecture, as I said, a continuous bag of words model and skipgram. What is word-to-vector consists of? This word-to-vector model, if you imagine, in a neural network, it's going to be a two-layer neural network architecture, wherein one input layer, one hidden layer, and one output layer. Those who don't know what is neural network is, I'll just give a general introduction about what is neural network. It is going to mimic the exact human brain functionality into machine. That's called neural network. So neural network architecture has three main layers. One is input layer, second one is hidden layer, third one is output layer. Input layer, as far as our concern, it takes all the input. As a human being, if we process the input from the environment, the the sensory organs what we have like hand, eyes, nose, everything will take up the information from the environment. That's called the input layer. And our brain has a lot of neurons which is inbuilt to process what the information is provided by different sensory organs. That's called hidden layer. And the actions what we do out of the information what we processed already is what the output layer, which is produced again through the use of sensory organs by human beings. Similar way, in neural network architecture of the PITS model, we have a three-layer architecture. So it is going to trigger out the actions depends on the input what is given and the weights what is produced on each input signal. So that's how neural network architecture works in. So here, this word-to-vector model can also uses neural network architecture with hidden layer. So in neural network architecture, hidden layer is the most responsible unit to process any kind of input, and output layer which is going to have an output. And so the neural network architecture what is given at the right hand side, if you look at it. So this is the neural network architecture simple diagram, where we can have n number of inputs starting from 1 to n, and in between we are going to apply a lot of functions. There are a lot of activation functions in neural network architecture. You can refer it, or in later classes, if we have some time, we could see what is neural network architecture, how it does. So in continuous bag of words model, this model predicts the current word given context words within the specific window. Let's say this context is about on a specific sport. So this input layer is going to tell about what the context is. Context here is a particular sport, let's say cricket. The output layer contains the current word, and the hidden layer contains the number of dimensions in which we wanted to represent the current word, what is represented in the context also. So let's say in further example, if you would like to see it, just check out, I'll show you. See, cat ate dash, fill in the blank. So in the specific corpus, if it is given like cat ate milk or cat ate mice or whatever given things, it is going to fill out the next word what is having most cosine similarity between the previous word spoken and the next word what is going to be predicted in the hidden layer. In this case, its food is what the expected predicted word by continuous bag of words model. What skipgram does is, skipgram, as I said, it's an inverse process kind of CBOW, where the input is going to be predicted, but output is given. So complete the word's context. In this case, it is the cat ate. There are three words which is predicted by skipgram. If you look at the continuous bag of words model and the skipgram model, here input is going to be simple. So skipgram predicts the surrounding context words within the specific window given current word. So the input layer contains the current word, and the output layer contains all the context words which is related to the current word. And the hidden layer shows the window, like in which dimensions the word is going to be predicted. So this is how word embeddings work in skipgram and continuous bag of words model in general in word2vector model. If we just look at the output here, cosine similarity between Alice and Wonderland, what is given 0.99. Let's say this continuous sentence, the cat ate dash. For this predictions made 3. Let's say food 1, and then maybe milk 1, and then next item cheese 1. Let's say all the 3 words are predicted for this continuous bag of words model. So for this context and the word what is predicted, all the 3, it's going to calculate the cosine similarity. Whose similarity is more, that appropriate word come to this COBW prediction output. So in this task, like we can identify the most appropriate word for the next as the next word, which need to be typed in the given sentence. So this is how word embeddings work. So word2vector model is very popular now. Maybe if time is there later on, we can also go through how a neural network architecture, what is the math behind it, and how the word is predicted also we can see later. It's just an overall view of how word2vector model works in. Some of the applications where word embedding of word2vector model is used are sentiment analysis, speech recognition, information retrieval, and question answering. So now the popular application is simple chatbot also, or Grammarly, and some of the plagiarism checkers also using this word embedding software, word embedding concept. And word2vector, we have seen these 3 bag of words, TF-IDF scheme, and word2vector model. We'll just see the code and then come back to named entity recognition of same thing. Okay, so here some of the packages which we need to install are BS4. BS4 is Beautiful Soup 4. It's a Python library. I just gave a comment line, what is it and why are we using it. So it is a library for pulling data from HTML or XML files. It works with our favorite parser to provide idiomatic ways of navigating, searching, and modifying the parse tree. So if anyone know what is parse tree, the given sentence is going to be divided into multiple entities with the help of noun, verb, adjective, noun, verb, adjective, noun phrase, verb phrase, determiner. So this is called, I think, POS tagging, parts of speech tagging. We had a discussion about POS tagging in the first initial classes itself. So parse tree looks like where it is going to have a noun, verb, adjective, noun, verb, adjective, or adverb. So anything it could have. Maybe later I'll show you how a parse tree look like also. And URL library dot request. This module is going to define its set of functions in the classes with the help of beautiful soap. We are going to open some of the URLs which contains the given text file. So for that, URL lib dot request is used. And this import RE, it is also a famous package which allows us to do some of the regular expressions. We had a session on regular expressions. In that also I had told you about RE. RE is a package which allows us to do all regular expression tasks. And as usual, NLPK, Natural Language Toolkit, this we are aware already. So in this, the article we are going to scrape is in the Wikipedia article about artificial intelligence. Let's write a Python script to scrape the article from the Wikipedia. So here, the URL which I'm trying to open is just directly from Wikipedia. And after the data is read, it is stored on a variable article. And then using beautiful soap package, we are just trying to convert them into pre-structure or POS tagging. And then we are identifying different like wherever past article find all P is pattern, and those P are identified as paragraphs. So after that, on each paragraph, we're trying to do some pre-processing things. So here in the paragraph, I'm just checking, I'm just converting them all into lower cases, and then tries to find out the regular expression starting with a to small z or capital A to AZ. So here the article which starts with an alphabet, and then preparing a data set, we will be applying a step called tokenization. We all of us know what is tokenization, dividing the given document into individual words, nothing but tokenization. So, and then after dividing the individual words as tokens, all the words are getting stored in the variable all words. And then normally we do pre-processing techniques, removal of stop words is done here. Then word2vec model is constructed with a minimum count. Let's say a word which consists of minimum count 2, or if the word is appearing twice, then we are just building a model word2vector. And here gensim is the package. From there we are just importing a word2vector model. So model, there are plenty. Word2vector is one among them. Gensim has even other two models also. We can look up what are the other modules in later stage. So I'm just trying out the word2vector, what are all available in the given Wikipedia page, and I'm trying to look out the word artificial, and most similar word I'm just trying out intelligence, and I'm just trying out for intelligence what all similar words or the next word can appear for the intelligence is what I'm trying to do that. So if we just run through this word2vector model, these two sentences is see, okay, the article is brief from the URL, and then here it's gonna be parsed. If you would like to see the paragraphs, you can check the paragraphs what are all available. So it's just listing out all the paragraphs, and then in that paragraphs we are doing some pre-processing things. So some of the pre-processing text is done, removing stop words. And afterwards, we are calling out the Jensen model. So we'll run till vocabulary, what all is available, and then tries to finish. If you look at some of the vocabulary words are given in the single quotes. If you look at neuron, weighted, weights, LXE, linear, these are all individual vocabularies which is used on the script page. And Grigorievich, Stephen. So all these are all individual vocabularies used on the script. And after which we are just calculating which are all the words are similar to intelligence. We are trying to find out. So for intelligence, what is the next word to be predicted is given with its cosine similarity value. So if you look at the answer of this page, AI has the most cosine similarity value is 0.65, and artificial is 0.64. Used human learning could, would, possible, may, one. So for the word intelligence, the next word to be appear or the relevant word which is relevant to this context is produced with a set of cosine similarity value. So we can write code that in the, maybe if you are building a Grammarly kind of software where I want to predict the next word automatically, we can have a corpus and then we can run through this model, and for any word which comes in the next type from the human being as a input word, that input word we can pass it here in this sentence, and after that whose cosine similarity value is higher, that can be a next predicted word can be shown in the list, and then user can select it. So as we type in the grammar in the Gmail also, we would see a lot of predictions done for us. We will be selecting out of that. That way, according to the cosine similarity value, whose similarity value is more, those set of words would be displaying in word embeddings. So this is the example of word embeddings with the help of word2vec model. If any doubts, you can just ask us for 2 minutes, and then we'll move on to LER model now. If any questions, questions are invited. Entity
This conference will
recognition.
now be recorded.
What is named entity recognition and where we can use some of the use cases also I will try to explain. So what is named entity recognition? It is kind of chunking again, but identifying the individual entities in the given text. So this is a famous popular technique in information extraction to identify, and we can segment all the entities and classify them or categorize them under a variety of predefined classes also. In any text or in any document, maybe there is a particular term that represent a specific entity, let's say a place name, or it is representing about a time, or it's representing about a famous personality, or it's representing about a particular food item. These are all individual entities. So these entities are known as named entities, which more specifically we refer them in the real world objects like people, places, organizations, and so on. Now we will be defining them in the parsing structure as proper names. And the naive approach could able to find out these by looking out all the noun phrases in the text document. So noun phrases are nothing but NP. When we do POS tagging, NP is very popular, could be identified with the help of this named entity recognition. If you look at this popular technique, how NER is going to work. First step towards the information extraction, and it locates and classify all the named entities into predefined categories such as names of persons, organizations, locations. So let's see in a real world question like which companies were mentioned in the news article. If we have a question like this or a query like this, we can just simply identify what are all the company names as recognized as named entities. We can just easily pick up and give a quick answer of for this question. Where specified products mentioned in the compliance or reviews. Let's say a product review is extracted from a Twitter or any of the social media place. And if I would like to check whether my product has been spoken in any of the reviews, I can just extract the name entity called the product name and then check how many were discussing about the product. Does the tweet contain the name of the person, or it contains any location, or it contains any food item name? So for all these questions, we can give an answer which has been asked dynamically, so that named entity recognition plays a major role to do actions on these questions. So for this or for achieving named entity recognition, the step is like we are supposed to import NLTK package into our environment, Python, and from that we can apply word tokenization, as we all familiar with this process. Then we are supposed to import the POS tagging. POS tag is nothing but parts of speech tagging, which is going to identify individual tokens as different uh, parsings. They are like name. If it is going to be, it's going to be identified as noun phrase. If it is a verb, it is going to be identified as verb phrase. So name phrase, which will be represented in POS tagging as ENP, and verb phrase are all represented in the form of VP. So information extraction sentence from, let's say an example here, it is given. The New York Times, European authorities fined Google a record of $5.1 billion on Wednesday for abusing its power in the mobile phone market and ordered the company to alter its practices. So now we are trying to apply word tokenization and parts of speech tagging to this given paragraph. We are going to get a list of tuples containing the individual words in the sentence and their associated parts of speech also. So for that, this code would help us to do parts of speech tagging on the given paragraph. Once that done, we are identifying the noun phrases first out of the POS tags. Noun phrase chunking identify named entities using a regular expression. So we are supposed to write some regular expressions to identify the noun phrase alone on the POS tags that indicate how sentences should be chunked. In the example, a chunk pattern consists of only one rule, that a noun phrase should be formed whenever the chunker finds an optimal determiner. I think we had a discussion about determiners what all in the previous class also. And in this example, the regular expression pattern, what is written here is a noun phrase, which is going to be followed with a determiner or an adjective or again a noun. So this is how a pattern, if it is appearing, I'm just extracting and then considering or chunking it as a noun phrase. Using this pattern, we can create a parser that could be tested on our given sentences. So how it's going to be done in the next step we will see. So in the previous example paragraph, what was discussed, the output can be read as a tree or a hierarchical tree with yes as the first level, denoting sentence. If you look at the parse tree, looks like this. So tree is going to have a root as yes. Yes denotes the given sentence, and it's going to be divided with multiple subtrees, where each subtree is going to have a single word in it. Let's say If a noun phrase is identified, that noun phrase is going to have a determiner dt and a noun, and all others are identified as individual words. And again, a noun phrase can also be identified with a single noun, or noun phrase can have multiple of things like determiner and an adjective and a noun. So this is how a parse tree looks like. So for the given simple input, the output is given at the left hand side if you look at it. So each word is identified with its relevant. See, if it is relevant, the JJ is represented as adjective. The authority is saying that noun phrases. Find is what the verb phrase, and Google is again a noun phrase, it's identified. So individual things are identified and then named with the POS tagging. This slash and after which whatever is appearing, it's called the POS tagging things. The IOB tags is a standard way to represent the sound structures in the files. So IOB tagged is used, which is come from the NLTK package. So if we look at the next thing, European is an adjective and authorities, and each individual is represented as, oh, if you look at it, all those are all objects. So here one token is going to be represented in one line, each with its parts of speech. So here the parts of speech is this JJ. So in each line we have one word. This is the word we identify, and which could be identified with the use of word tokenization. And this JJ indicates the parts of speech, POS tagging as we say, and the named entity. This is the named entity identified. So IOB tagging is the process in which we are going to identify the tags what is available for this particular object. So based on this training corpus, we can construct a tagger. It can be used to label all the other new sentences also. Whichever you give it, according to that, it is going to identify the named entities what is available. So we had used a simple pattern recognition, regular expression to identify the noun phrases and then identifies the individual objects. So I use the NLTK chunk and this tags to tree function to convert the tag sequences into a chunk tree. And function, this chunk can recognize the named entities using a classifier. The classifier adds the class label as person. If the people name something is given in this, it could be identified as a person. If any organization, like say an example, Google is given, it could be identified as the category name as organization, and GPU, any values are given. So it keeps going and identifying the named entity tags like this. And but if Google is recognized as a person, it's quite disappointing. If you look at this output here, Google is identified as a person, so the category is not properly given. So what are we supposed to do? So in this we have a special package name called Spassy. Spassy also will allow us to do the same kind of named entity recognition, and it supports the following entity types. The entity types are given here. If you look at person, it is identifies the people, including the fictional characteristics also. If it is imaginary characteristics, that can also be identified by person tags. And NORP, which identifies the nationalities, Indian or Pakistani, whatever we represent, those nationalities could be identified. And religious or political groups, whatever available, could be identified. And FAC, all things, airports, highways, bridges, etc., could be identified. GPE, all the countries, cities, states, location, law, some of the national law named law documents, languages, date, time, percentage. If it is include the percentage symbol, then it could easily identify. Then some of the cardinal values ordinal values and the quantities, money value, everything could be identified with the SPASI package. We can also try out with the SPASI package also. The code it's also going to be discussed, and then I'll pass the code to you. You can also have a look at it. But the nice thing about SPASI is we only need to apply NLP only once. The entire background work will take care of the object identification and returns it very easily. So how to install SPASI package in Anaconda platform is you can go to Conda prompt and then type in Conda install hyphen SPASI. Then you can try installing this. You can do this code and identify. See, using SPASI, you don't need to set up a pattern at all because you don't need to have a regular expression thing to do it. SPASI has all the set of words built in corpus where it is identifying the individual words easily. So only thing what we have to do is we need to do some pre-processing tokenization we have to do, and then all these tokens need to be passed with its POS tagging to the SPASI builder, and this SPASI builder will identify individual words with its particular entity. So in this example, for the given text, European is NORP is identified, the nationality is given, and Google is identified rightly as organization, and wherein the 5.1 billion tells about the money value, it's given as money, and Wednesday it is identified under a parameter called a date. So this is a named entity recognition usage, and this is again BILUO tagging. It is kind of token level entity annotation where B is what beginning of the given text, I is what inner token, L is what last token, and U is what unit or a single token where it does not have any more words in it. And it is not at all a token, non-entity token, which is represented as O. So in the previous example, we were working on the entity level. In the following example, we are demonstrating token level entity annotation using a BILU tagging scheme to describe entity boundaries. Boundaries in the sense like it need to look at only these set of entities. It need not to look out the entire entity. So you can set up this is the beginning entity and this is the last entity. So within that, it need to identify what all individual tokens are there and it need to tell us. So if we have a look at B in this, identifies the beginning or it begins the entity where it starts with the European as a word. And if I means that it inside the entity, inside the boundary, what are all the words are available, those things. And O means it is outside the boundary. So if some of the things like mobile phone market and all these are all those are all, yes, those are all O, which identifies outside an entity. And if it is an empty thing given, then it is identified. There is no entity in this set. So from an article, how do we extract the named entity thing is discussed in the code. This is how it is going to identify the tree, and then it says that what is the POS tagging. If you look at firing is a verb, it's a pronoun, it's an adverb, it's a verb, determiner. See, if you look at firing, as we all know, this is a kind of parse tree which looks with determiner, adjective, noun, and the adverb, pronoun. This is also pronoun. So this is how parse tree looks like. The result of NER model would look like this. So we'll directly see the code and then come back. So here some of the packages which are module which we need to include are word tokenization is a module, POS tagging, and regular expression parser is also included here. And EX is the word what is available. So we'll just extract the sentences and see. So here the sentences are given with the POS tags. You look at practices, noun and the determiner company noun is given. And I'm looking out the pattern. So this was discussed already. Just a pattern is given, and then it's going to tell us the parse tree. You look at it is parsed already. Then this IOB tagging is done. See, individual tokens are identified with three entities. One is the particular word, and then TO is the parts of speech. PO is tagging, and this O is what the particular entity name object. This was a simple pattern identification. We did it, and we did it with the simple IOB tagging. And where if you look at here, in this we had a problem like this was the problem. Google is an organization, but which was identified by a person. Because we wrote something pattern with a regular expression thing wherein noun phrase need to be identified if there is a determiner next to it or not. So by then it's identifying Google as a person. So we are directly moving to the SPACY package and then running the same thing. So Google, it is identified as organization because SPACY consists of all the words and its relevant entities into it. We don't need to write any pattern for it to identify the individual entities. It has its own set of entity list into it as a default. So that's called a collection. So collection from that it's just checking the individual words, whatever we did it, and then it tries to identify the entities out of it. So if any more doubts you can ask, or I can share these two files. You can also and then ask your or post your doubts in the group itself. Any other doubts, guys?
Hello.
Yes, Sandhya.
Yeah, Ambika, I just had a doubt in the previous session. We have discussed two methods, CBOW
Yeah.
and the histogram, right? So, like, when to use which one? Like, what decides which one should be taken?
Okay. Let's say if we look at in the word embeddings, you would like to find out the next word. Advice is to go for CBOW.
Okay,
And you have many words are leftovers, but you are not able to find out. Only two words are there where you can go for skip gram because
okay,
gram tries to identify um, next words like relevant to that particular word. Correct? Gram in the sense we can go for either 2 gram or trigram or n-gram. It depends
right,
on number of words missed out in the particular text.
right,
You
right.
can gram. But in you would like to find out one next word in the given sentence, then we can go for CBOW.
Okay. So we can give the command, or it automatically takes that which method has to be taken.
No, you have to give the command.
Okay, okay, okay. Got it.
We have
Thank
to give
you.
the command. Yeah.
Okay,
I can also share the code. Please try out the other things also and post your queries. We can. I'll also try to find out the answers for that. If any more
okay,
questions.
okay. Yeah. Thank you. Thank you, Ambika.
Thanks, Cynthia. Any other doubts?
No, not at my end.
Okay. Okay, if no more questions, then I can wind up the classes for today. And if anybody would like to have a next session on machine learning news, fake news classifier, we can think about it in the next week. Else, with this, I will complete NLP classes, and
Yeah,
I'll share the remaining materials also in the Google Classroom.
okay.
Thank you,
Yeah,
guys. Thank you
definitely.
so much. Yeah, please.